Thanks everyone for joining today once again to another quantum computing meetup. So today we have Dr. Jonathan Wurtz speaking to us today on dual mode quantum computing. Seems like it's an analog and digital gate-based quantum computers, which he'll be able to tell us today how it can be especially powerful in machine learning, optimization, and simulation problems. A little bit of background on Jonathan Wurtz. He got his Bachelor of Science in the University of New Hampshire and finished his Ph.D. at Boston University. Did a brief stint at the research at Tufts University, and now he's a senior researcher at QuEra, which is a company that is known to build quantum computers based on neutral atoms. So, ladies and gentlemen, without further ado, Jonathan Wurtz.
Thank you. All right. Can everyone see my slides?
Yes.
Good. All right. Thank you very much for the introduction. Today, I would like to share some of the work and results at my company, QueRa Computing, which is developing neutral atom quantum computers and has, in fact, neutral atom computers available today on Amazon Web Services Cloud for everyone to use, as well as hopefully have future upgrades towards for quantum practicality at every step. Today, I'll be presenting on, again, dual mode quantum computer and its applications. So first, a little bit about QueRa Computing. We build quantum computers, and specifically, we build neutral atom quantum computers, which use atoms as the host of qubits. We have built a machine which has up to 256 qubits, fully coherent qubits, and is publicly accessible on Amazon Bracket. This machine is called Aquila. A picture of it is right here. We have many people who are already using our computer, both through Amazon Bracket, where we have the very interesting experience of not actually seeing what our customers do, as well as interactions directly with customers, developing solutions and applications for their particular problems and interests. One thing that we are very interested in doing is focusing on achieving an amount of Sorry, I just got muted. We are interested in achieving usefulness at every stage of quantum computing. Today, we have a limited but fully coherent computer, but we are hoping in the future to expand the capabilities towards the holy grail of large-scale, error-corrected quantum computing devices with thousands or tens of thousands of logical qubits, or of physical or logical qubits with very precise control over gates. Our company is built on outstanding scientific foundations. We are built out of ideas based from the lab of Misha Lukin in Harvard University, from his work on neutral atom quantum computing, which started many years ago, as well as several other professors from both Harvard and MIT. Now, a little more about QueRa. We are focused on best use of our quantum computers, and how we do this is through tight integration of both hardware, software, and applications. And the idea is we hope to have some measure of co-design in that we figure out which near-term problems can best be tailored to our particular brand of neutral atom hardware. This includes things such as unique algorithms for optimization, machine learning, and simulation, some of which I'll go over later today, as well as software such as Blockade, our high-performance tool for emulation to test small-scale quantum programs, as well as the base, which is our neutral atom hardware, which is flexible, large-scale, has interesting features, and as part of the idea of this tight integration, we can iterate our hardware upgrades as we identify better use cases for hardware, which is where perhaps everyone here on this call may come in. Our first flagship computer is called QuEra, which is a neutral atom quantum computer with up to 256 neutral atom qubits with coherent evolution throughout the entire computation. This computer has a slightly different mode of operation than the prototypical quantum computer in that it's something called dual mode, where today it is an analog-based quantum computer, which is a non-universal but still flexible and powerful mode to do computation, which I will detail a little bit later. We like to call this computer a field programmable qubit array, in the sense that just like a FPGA, field programmable, just like an FPGA, we can very specifically program all of the bits and pieces of our device in order to execute quantum computations. A second product that we have is something called Blockade, which is a high-performance emulator, which we use as a testbed and interface for neutral atom algorithms. It's a tool developed in Julia. We built it in Julia so that it can be high performance and efficient, so that we can focus on large-scale quantum simulations on large numbers of atoms. It's very reasonable to ask for full state vector simulation of 16 to 20 qubits, runs very quickly. We have support and focus on applications such as high-performance computing, cluster computing, GPU support, and everything in between. The idea here, again, is we want to be able to let people have a tool to understand how these quantum computers work before you can, as you develop your application, either for application on today's hardware or looking forwards to the dual mode computers of our future. Great. So with that, our two main products of QuEra and Blockade. Perhaps I can spend some time introducing how neutral atom quantum computers work. Now, neutral atom quantum computers have three basic building blocks: atoms, optical tweezers, and something called the Rydberg blockade. So at first, we have an atom. And what we do is, this is, say, some atom floating in a dilute vacuum, in a vacuum cell. And we turn on a set of lasers, which act as a set of laser tweezers, they're called, which hold and trap the atoms. Now, what we can do is this atom floats around and eventually is captured by the laser tweezer and held in place. We can actually image these individual atoms with a camera through fluorescence. So this picture here is actually a picture of an individual atom in one of these laser traps. Then what we do is we identify two states of the electronic orbitals of this electronic orbitals of the valence electron of this atom, mainly the 5s ground state of the atom, as well as a highly excited 70s state, which encodes our ground and excited state qubit. This excited state, the 70s, that's a basically very large quantum number, which means that the atom sort of puffs up. And this is what enables interactions with adjacent atoms, as well as entanglement. Now, what we can do is we can turn on a very precisely controlled laser, which we call the Rydberg laser, which drives transitions between the ground and this excited Rydberg state. And what this does is, I guess, as the animation just showed, it grows your atom between your ground state, which is small, and your excited, puffed up Rydberg state. Now, the advantage, of course, is that we can add many atoms. So, for example, we can consider a second atom in another trap nearby, again, individually imaged and addressed and held with laser tweezers. And we can do these same dynamics where we drive the ground Rydberg transition and and oscillate between the two. Now, the final key building block of neutral atoms is something called the Rydberg blockade, which is due to this something called the Rydberg interaction, which is a state-dependent energy shift, which depends on the 6th power of the distance between the atoms. And this typical distance is between 1 to 10 microns. And the idea is if you have two atoms in the Rydberg state, if they are within some distance, there is a strong energy shift between these two atoms. Now, if they're far away, the energy shift is small, and the two atoms can oscillate between the ground and excited state independently. However, if they are well within the interaction range, then they exhibit something called the Rydberg blockade, which is that when we drive between the ground and Rydberg transition, the state-dependent energy shift blocks adjacent atoms from both being in the Rydberg state, which means that what we can do is make it so that either one or another of the atoms is in this excited state, but not both. And what this means is that this allows us to remove this doubly excited Rydberg state from the dynamics entirely. And this, which means that the entangling dynamics do not come from the interaction itself, and instead come from the underlying blockaded Hilbert space. And by blockaded, I mean this is this Rydberg blockade, where the Rydberg blockade, of course, is one atom blockades the other atom from going into the excited state. And this is the key insight, and gives us a lot of stability in our dynamics, that we are insensitive to the particular value of the interactions because we're encoding dynamics in the Hilbert space and not the underlying interaction. Great. So that's our qubit, and this is how we do our interactions. A second part of our computer is something called analog quantum computing, which is a slightly different mode of operation. And here, instead of having a set of gates, what we do is we have user-defined waveforms for different parameters in a time-dependent Hamiltonian. So here, this is our time-dependent Hamiltonian. We have some drive term, which is this laser field. We have a detuning term, which sort of sets the value of the ground or excited state. And then we have this interaction term, which is dependent on the position of each atom. Then what this does is we have this time-dependent Hamiltonian, which we can use to define our evolution. And then we do, I like to call it an every-body gate, right? You have a one-body, two-body, every-body gate, where you start in some initial state, then do your time-dependent dynamics on every qubit, and then do some readout in the Rydberg basis. Now, this analog quantum computing mode is nice because it's flexible in terms of what these waveforms can be. For example, I can imagine a set of stepwise pulses, which might execute a series of gates, or I can imagine some set of smooth pulses or waveforms, which define an annealing protocol, which is a prototypical quantum algorithm to prepare ground states of quantum systems. Or perhaps I can do something even more exotic, such as completely arbitrary user-defined waveforms. For example, maybe I do some funny flow K type thing, and then I do some slightly gate-like thing over here, and then maybe I do an annealing protocol in the end. Whatever it is, this is a flexibility that is left to the user. Now, the second part of this analog quantum computing is something called programmable connectivity, which is that we are able to encode problems in the spatial positions of the atoms. So, for example, here's a picture of, I believe this is 121 atoms, individual atoms arranged in a square grid, right? And we can position all of these atoms and do dynamics on them. However, this positioning is arbitrary. For example, here is a square grid, but I might imagine, say, a Kagome lattice for physics, or perhaps even the coastlines of the world in order to encode some optimization problem. And in this way, we're able to very quickly change what the positions of the atoms are, even shot to shot in our machine, so that we can very quickly and dynamically update what we want our programs to be. So then here is a picture, which is Aquila saying hello world, which is basically a picture of many, many different atom positions, which makes it look like hello world is scrolling to the left. Great. So this analog quantum computing mode is slightly different than the prototypical digital operation mode. And it has several advantages and a few disadvantages. Perhaps to start with the disadvantages, the analog quantum computer is not necessarily a universal machine. We only have a global control over this Rydberg drive, which means that our dynamics are like go on every atom at once. However, what this does mean is that because the interactions between these atoms are always on, this means that we get a much faster spread of entanglement and correlations over an equivalent digital gate-based machine, which might need to execute a series of, say, Hadamard's and C0 gates in order to build up entanglement and correlation. Furthermore, this analog computing mode, especially for things like quantum simulation, annealing, and other dynamics, ends up being robust and stable to fluctuations in the particulars of your Hamiltonian. Because in the end, what you're doing is you're just doing time-dependent dynamics, and you can even use that noise potentially as a resource for your time-dependent dynamics. For example, if you want to think about slightly open systems and so on and so forth. Now, today, our quantum computer only works in this analog mode, right? We do not support this digital gate-based mode because we don't necessarily have local addressing or other support for it. However, what a future upgrade is, and this is the title of the talk, is this dual mode operation. And the idea of dual mode quantum operation is you start with some initial state, and you can alternate between a series of gates and analog dynamics. And in this way, one might be able to imagine, say, I prepare some particular initial state, I do some analog computation on that, and then I read out that analog computation in some different basis, depending on the set of digital layers, or even alternate between analog and digital layers to execute more interesting quantum programs. The idea here is that the flexibility is left to the user in terms of defining what these waveforms are, and defining the waveforms as well as defining the arbitrary positioning of the atoms. Great. So this is how our machine works in this analog mode where we do nonequilibrium quantum dynamics or quench dynamics or whatever we want. And now what can we use this for? So now I'll go over some key applications of our neutral atom hardware. We have identified 3 major areas where Aquila may be able to solve problems. These 3 major areas are machine learning, for tasks such as classification, regression using reservoir computing. The second is optimization. There's a favorite problem which maps very nicely to neutral atom computing called maximum independent set. Basically, it maps very nicely to this Rydberg blockade. But we can also do other encodings, which enable us to do things like QUBA, which is quadratic unconstrained binary optimization, graph coloring, maximum click, and other optimization problems. And then finally is the application of simulation. And this is based off of Richard Feynman's idea of using a quantum computer to simulate quantum effects, where we, for example, can evaluate quantum phases of matter on Rydberg systems or analog systems, analog with a UE instead of analog, as well as things like non-equilibrium dynamics, thermalization or athermalization, lattice gauge theories, and other interesting and exotic phases of matter or behavior. Great. So our first key application is machine learning. Perhaps to contrast with classical neural networks, what we do is we have some series of input layers, some series of hidden nodes, and some set of outputs. And then we do backpropagation based off of, standard tricks where you have input data and you say train on labeled data and so on and so forth. This has billions of parameters. This training may be expensive or maybe very data hungry and so on and so forth. Now, what we are doing is a slightly different approach called reservoir computing. And the idea here is we replace the hidden hidden layers of a neural network with something called a quantum reservoir. So here we have some encoding of our quantum system, and we do dynamics of this system. And if our system is, I guess, chaotic or ergodic enough, this lets us encode the inputs into the dynamics of the state and the final state of the system. Then we can take a measurement reading of that outcome. We do some simple post-processing on that and learn only on the post-processing in order to do classification, regression, and other machine learning tasks. The key idea here is that there is no quantum training required, which means that more or less we do not need to do any gradient-based methods on variational parameters in our reservoir. So this is very quantum efficient in terms of the number of samples in order to do your learning. This reservoir computing is also already successful in many other areas, because more or less the idea is if you have some chaotic system, say the weather patterns over the United States, or say the stock market or something, that if you have a sufficiently chaotic enough system, and that's sort of briefing over the exact specifics, then you are able to match the dynamics of your chaotic system to the dynamics of your other chaotic system in order to, for example, do prediction. So we could do reservoir computing with neutral atoms by choosing a particular encoding. For example, if we want to classify pictures of horses, what we can do is we can downsample this picture and then encode this downsampled picture into the local detuning of each atom. So this is, we choose this delta term for each atom based off of this sample. We then do quantum dynamics on these samples, take a measurement readout, do a classical linear regression step, and then use this to do our classified data, or classify our data. Now, again, the key idea for this is that the learning step on this, which is basically finding the weights and biases of this one layer neural network, is very quick and efficient. Now, as a first example of this, we did some demonstrations on everyone's favorite MNIST data set, where you try and classify different digits into their numbers. And here are some initial results where the y-axis is the test error rate on this MNIST data set, and these four are classical neural networks, and these two are two quantum versions. The right one is if we do not include any entanglement, which is that all the atoms are very far apart from each other, which is sort of a classical limit of this machine learning algorithm. Whereas the quantum version is if all of our atoms are very close together and have some entangling dynamics between them, which indicates that this quantum behavior is a key resource for doing our learning, and in fact gives us results comparable to sort of standard neural networks for this problem. Great. A second key application is something called optimization, which is my particular favorite. And one example of this optimization is called maximum independence set, which is a graph-based optimization problem. So suppose you have some graph of vertices and edges. The challenge of this combinatorial optimization problem, which is to say that you have an exponentially large amount of solutions, and you want to find the solution in this exponentially large set, which maximizes some objective function. You want to find the subset of vertices in this graph such that no two vertices are adjacent. So you can see here that these red vertices are this maximum independent set, and in fact are an independent set, and in fact this is the maximum independent set of this particular graph. And this problem very naturally maps to the Rydberg blockade, where we equate the Rydberg state to the independent set state. So as a demonstration of this, we can use Aquila to solve, as a prototypical example, possible locations of shops or antennas or whatever locations in Manhattan. So here I have some graph, which is just synthetic data of locations where the vertices encode this independent set constraint. Then we can use our arbitrary atom positioning to encode the problem. So this is now each atom corresponds to a single vertex in this graph. And then we excite the atoms. In this case, we use classical quantum annealing, or the adiabatic algorithm, to prepare the ground state of our system in order to find the answer to this combinatorial optimization problem. So then this is the maximum independent set of this particular problem. Great. Now, as a final key application is simulation, which is what this computer was in some ways born to do, because this is what our academic founders at Harvard first built these machines for. So the idea here is we can use the machine to simulate the dynamics of Rydberg atoms. Or instead of just Rydberg atoms, we can use it to simulate a similar system. For example, condensed matter systems, solid state systems, and so on and so forth. As one example is exotic phases of matter, such as quantum spin liquids. This is a paper from 2021, which shows this quantum spin liquid physics, which is more or less, you have a degenerate ground state of dimers, which undergo non-trivial dynamics, and you end up getting a very interesting ground state out of this so-called quantum spin liquid. A second example is non-equilibrium quantum many-body dynamics, which is when you quench your quantum system and it executes interesting quantum behavior, which only depend on, which independently depend on entanglement and superposition of the state. So, for example, there's a famous paper in 2017, which in fact sort of kickstarted the whole revolution for neutral atoms, which did quench dynamics of a particular Rydberg state to find the particular Rydberg states show athermal behavior in their dynamics, which sort of kickstarted an entire field of thermal and athermal dynamics. And then finally, you can also use the system to simulate quantum phases of matter. For example, using an adiabatic protocol to prepare interesting quantum ground states. For example, here, this is from a paper in 2021, where we, by varying the lattice spacing, or the distance between each atom, we are able to prepare different phases of matter. For example, here is some checkerboard phase where you have an alternating Rydberg ground, or say a striated phase, which is sort of a second nearest neighbor, or perhaps even more interesting star phases, which is a explicitly quantum phase, which has no classical analog. Great. So those are the key applications, but of course, we are not done with our adventure. We are very interested in scaling and making these machines as best as we can. And we believe we have a strong path forwards, both to NISQ era utility, as well as towards our holy grail of fully error-corrected, fault-tolerant computing. One of these may be, for example, massive scalability. So right now we chose up to 256 atoms, because I guess 256 is a nice round number, but nothing is stopping us technologically from scaling to tens or hundreds of thousands of qubits. We are only really limited by the amount of laser power. Basically, each spot, each trap requires, a few milliwatts of laser light, and then now a few milliwatts times 10,000 is suddenly a relatively large number, which then means that we are able to scale up to a very large number of physical qubits, which of course means that we may be able also to scale up to a large number of logical qubits without the need for interconnects. A second key advantage that we have is because our atom geometry is flexible, we're also able to move our atoms around mid-circuit. So, for example, this is a picture from our collaborators at Harvard from last year, which shows an atom moving protocol where we move a set of atoms around, and with each red circle is a set of quantum gates. So this lets us do all-to-all connectivity of quantum gates in order to execute digital quantum operations. And what this means is that we can also very efficiently scale without necessarily needing a huge number of control lines and so on and so forth. All we need is a set of lasers and basically fine control over these atoms. And in fact, this animation here also shows that we can do things like error correction. So actually, this animation was a demonstration of the toric code, which is the toric code of a torus, which is a way of doing error correction, which you can't necessarily do on like the 2D geometries, which are inherent to, for example, superconducting systems. Where here we're able to try out interesting and exotic codes, as well as things like the toric code, in order to implement error correction for fault-tolerant quantum computing. And this is another demonstration by us and our collaborators at Harvard, which came out in 2022, which suggests that, in fact, we do have a path forwards to error correction. Actually, a recent paper which came out shows that we are able to get 2-qubit fidelities upwards of 99.5%, which is starting to get close to error correction threshold, which is very exciting. So perhaps to conclude, I'll first think about our quantum roadmap. So what we are focused on today is quantum value creation, right? We have a quantum computer, we have a coherent quantum computer, and we have the largest quantum computer, coherent quantum computer available on the cloud. And we want to use it. We want to solve hard problems at the edge of computation with it. And we believe we're able to do it. And I guess I invite everyone here to think about ways that they might be able to do it. Now, this is what we can do today. But as we move forwards, we need to also think about how do we best engage and use this computer to solve problems using NISQ era, or noisy intermediate scale quantum era computing. And this is things like individual control, this dual mode operation, native multi-qubit gates. For example, we can use this Rydberg blockade to do a 3-qubit or 4-qubit gate, long coherence of these qubits. And then as we are iterating and adding features to this device, focusing on our the holy grail of fault tolerance with error correction, tens of thousands of atoms, and high fidelity gates. Great. Now, if you're interested in learning more or working with us, we are happy to provide more information. This usually comes in 3 pieces. One is solutions. So this is world-class experts. I guess that's me. Which lets us try and understand how your problems or your applications may fit on today's or tomorrow's quantum computers. The second is premium access. So we have our quantum computer available on Amazon Web Services Cloud, but very often, and this is one of our big comments that we get, is our queue is very long. So premium access potentially lets you bypass the queue, get expanded access, talk with experts in order to understand understand underlying problems. And then finally is machine sales. So we are in the process of building many quantum computers, and you may be able to get one for yourself. Now, if you're interested in learning more, please feel free to contact us to discuss a wide range of collaboration options. In the meantime, I would like to thank you for your time and attention, and would be happy to answer any questions you may have.
Hey, yeah, thanks, Jonathan. Great talk. Here's great summary. Yeah, just did anyone have any? Well, yeah, I guess Ron had a question. Oh, actually, David had a question first. He was asking any application examples of dual node quantum computing.
This is a great question. So as a disclaimer, we do not have a dual mode quantum computer today. right? We only have this analog mode computation. However, one might be able to envision if we have this dual mode computer, this lets us, for example, in the beginning, this might let us do a set of digital gates to do state preparation, and then do a set of analog entangling, a set of single qubit digital gates, and then a set of digital mode or analog mode evolution in order to quickly spread entanglement. So this might be extremely useful, for example, for things like error correction, machine learning, sorry. Or, for example, if we do a set of digital gates at the end, then maybe we can do things like classical shadows or other interesting things, which also lets us better characterize, for example, simulation algorithms, optimization algorithms. There are, I guess, many different applications. And I'm sorry if I'm not being particularly precise, because there are just a lot of things to do with it.
Yeah, another question by Ron was, are the neutral atoms and analog components separate hardware?
So I guess it all comes as one package. So hang on, let me go to that. Sorry, my screen is on the wrong. So the analog quantum computing is not necessarily exclusive to neutral atoms, and neutral atoms are not necessarily exclusive to analog computing, because in principle, every quantum computer is an analog computer. It's based off of a series of pulses, and you just very finely control these pulses in order to execute your computations. We are just giving you the full flexibility to choose different sets of gates. So in this case, the analog mode is more or less, you are basically programming the amplitude, phase, so on and so forth of our lasers, which are executing your quantum computations.
So if I could just follow up on that, is my question was, are they separate devices, or is it just this one device being operated in dual modes?
This is I see it. Yes, this would be the same device operating in dual mode. Yes. And this is basically because we can imagine the series of gates is just one series of pulses, which we've wrapped the Hadamard gate is this series of pulses. And we can very easily switch between them because they're more or less the same lasers. We're just add a few extras. It's a great question.
Thanks. If I could ask another one. So did I understand that you have the analog version of it working, and you're working to get the neutral atom capabilities going?
So this is a neutral atom quantum computer. So the neutral atom is the host to the qubit. And the analog mode is basically how we do the manipulations of that qubit hosted by the neutral atom. So it all sort of is one package together.
Great. And can you talk a little bit about what the topology of the neutral atoms would be? Is it like a 2D grid, 3D grid? And for like 256 neutral atoms, what's sort of volume of space? And I assume you're suspending them in a vacuum, right?
That is correct. So one of the key advantages of neutral atoms is very flexible geometry. So for example, here we have a picture of, here we have a picture of a bunch of atoms which are arbitrarily positioned in space, which lets us potentially even shot to shot change what the geometry of our atoms is. We choose a two-dimensional geometry. The area is 75 by 75 microns, which is where you can put the atoms. And the typical interaction distance is between 4 to 10 microns. However, beyond simply having this fixed geometry where we place the atoms arbitrarily in space, we also have this reconfigurable geometry where we were able to move atoms mid-circuit. And this means that for a digital gate-based machine, we are able to have an all-to-all connectivity by moving atoms and therefore the qubits around in space in order to execute gates.
Very cool. So, but there's nothing to stop you from implementing three-dimensional grids, right?
In
Say nothing. Say
principle,
nothing.
yes, it is. It's a little bit more complicated to do, and
Sure.
we didn't necessarily see the advantages of it, but nothing is stopping us from doing 3D. Yes.
Okay, all right. This is my last question. I'll let somebody else go. I see on this thing that you're showing now that you're moving atoms as groups. Are you able to move them one by one, and can you just arbitrarily make groups?
Yes. So we are also, this is for this particular example, we move them as a group, but we're able to take our laser tweezer, and basically what you do is you just use a laser to pick, you can pick up individual atoms and move them around. But then of course, if you want lots of gates happening at the same time, then you want lots of atoms moving around at the same time. So in that way, it's more efficient, just move many around at once.
Awesome. It's been a real pleasure being able to speak with you directly. Thank you so much.
Yep.
Yeah, well, moving on, Ulrich had a question. Is there an easy way to convert my digital gate-based code into an analog Hamiltonian for Eureka?
Unfortunately, it's a slightly different paradigm of computing. So this means that sort of the standard gate-based intuition does. Let me pull out the standard gate-based intuition doesn't necessarily roll over for analog mode. And this is because, unlike digital mode, your atoms are always interacting with each other. So this means that when you're doing your dynamics, you need to be very considerate of the fact that your interactions are always on. However, this does mean that things such as state preparation. So for example, if you want to do a VQE type algorithm, a variational quantum eigensolver, to find ground states of some system, typically what you need to do is you need to trotterize some Hamiltonian and just do your dynamics on that trotterized Hamiltonian. But because we are doing analog computing, we do not need trotterization, right? We are able to directly encode entanglement at all times, which means that trotterized dynamics are much more efficient to do on an analog device. This is a great question.
Okay, another question was, can you tell, well, yeah, could you tell about the stability of your quantum computer? How long can it operate without failure?
I guess there's two answers to that question. One is the coherence time of the system. So here we have through Amazon Bracket, we have a total evolution time of 4 microseconds is the maximum you can do. And if you count the number of Rabi excitations, which is more or less the number of gates you can do, this corresponds to a gate depth. And again, you need to be a little careful comparing gate depth for an analog device, but this gives you a gate depth of about 60. Excuse me, sorry. If you look at the total coherence time, which is more than 4 microseconds, then you get a gate depth of about 60. So this tells you about the stability of the device. Now, I can't say the stability of our device. Obviously, it's stable. We're able to operate as a cloud service, which means that during our cloud service operations, our machine is stable. But I can actually tell maybe one small story, which is for the Harvard lab, which our device is built out of. They're able to just sort of run this thing nonstop for days at a time. Everything is a solid state piece of equipment. I guess there's like a few like shutters somewhere, but basically it's, you just turn it on, you calibrate it, and it's just able to run. So that's a great question.
Yeah, another question. Will dual mode QC be added into Blockade soon? So I guess when do you guys expect it to have the dual mode operation?
So this is for Blockade. Blockade. Actually, in principle, you are able to add it in, but it takes a little bit of wrangling. Right now, our scientific software team is actually working on tools to make this wrangling, which is more or less just like you're able to implement based off of the quantum register. You're able to execute digital gates on this register. But our scientific software team is actually in the process of working on this dual mode simulation with Blockade. So it's
okay. Another question was, how efficient is the dual mode quantum circuit compared to the quantum error correction code?
Well, a dual mode device is an inherently NISQ era device, which means that you cannot use error-corrected qubits. Typically for error-corrected qubits, you only have a limited gate set of, say, C naughts, or say maybe the Clifford gate set plus T gates is one prototypical example. However, for NISQ era, which means that you can get much larger number of physical, you can use a much larger number of physical qubits, you always need to be careful about and conscious of the noise and decoherence inherent to the device. So analog sort of gives you the maximum amount of evolution in quantum dynamics for a given set of decoherence. But unfortunately, it's incompatible with error-corrected and fault-tolerant computation.
Great. So Ulrich asked again, is there something like a simulator for Aquila so I don't have to wait for the queue to get my code right if he doesn't have
Yes. That would be Blockade, our high-performance emulator, which is written in Julia and supports HPC, GPUs, and other high-performance computing. The idea here is you have state vector simulation, where basically your evolution is some vector times some very large sparse matrix, and you're able to simulate the wave function as a function of time in order to do your analysis for your computation. However, this comes at the expense of the state vector emulation is exponentially memory or time intensive. So you're only able to do up to say 20 or so qubits with up to 30 or 40 if you pull a few tricks that we've done with Blockade. But this lets you run your small quantum simulations as well as submit directly to Amazon Bracket to Aquila through Blockade. So once you have prepared your particular state or your particular dynamics, it's a very simple command. Just say submit to Aquila, get your results from Aquila, and then you're able to compare your hardware results from what you expect.
Okay, great. Another question was, Vanek asked, in machine learning, can you support programmable statistics for training?
Could you maybe clarify that a little bit?
I guess, well, I don't know. The follow-up question to that was, is there a maximum number of pixels? Can you support multiple pixel layers as part of the calculations?
Oh, I see. This is for the, let's see, let me pull out the slide. Yeah, okay. So, so the idea of reservoir computing is in encoding your input into the quantum dynamics of your output. So this is a very, very flexible way of doing your encoding, and in some ways requires just the creativity of the programmer to figure out what a good encoding strategy might be. We just found that when you take the principal component analysis of pictures and use that PCA to encode the picture in the local detuning of the atoms, this found good results. But for example, if we have a different data set, say, I don't know, stock market data or something, then there might be some other more efficient representation of that data with a particular different encoding, which also might be enabled only by this analog mode computation. For example, I might picture, here are the wiggles of the stock market, and I can directly encode the wiggles of the stock market of that signal directly into the waveforms of the drives of the atoms, for example.
Okay, great.
Yeah.
Oh, sorry. Do you want to say something?
Yeah, if I can clarify a little bit. So in machine learning, typically you're going to be choosing different statistical programs in order to get the best results. It's not just looking at the image and determining what the image is. It's also being able to classify it based upon different statistical programs. Can you support different programs, not just to get the image and represent the image and identify it, but also as a means of optimization?
Ah, yes. This is, I did not show this, but we're also thinking about machine learning for optimization type problems as well. So here I also described supervised learning for regression, for classification. We can also imagine, say, unsupervised learning, generative modeling, time series analysis and prediction, regression, all sorts of other tasks, all sort of fit into this bubble of reservoir computing.
Okay, that sounds great, but can you use different statistical programs? I mean, can you enter your own statistical programs for what you're looking to find?
What do you mean by statistical? What do you mean by statistical program?
So if you look at some of the different statistics that are used in order to sort the data, you have to kind of play around with it in order to find the best way to identify what you're looking at. Is there a way of doing that, or are you limited to only one program?
I see. So I guess yes, and this is probably part of this design process of these algorithms, where you want to make sure that you are getting good performance. So there's sort of a very slow outer optimization loop, which is the programmer themselves, or maybe a machine learning agent, for example, trying to optimize what this protocol is based off of an understanding, say, of what the input data is, say, shuffling of the input data, the structure of that data, the structure of the output, and so on and so forth. But we are, it's all right now a very simple way of doing things, where we don't necessarily have some encompassing package, but it's more of a method in order to do this computation.
Okay, thank you very much.
Yeah, thanks for Vanek. Thanks for jumping in there and clarifying. Bettina had a question: which size of combinatorial problems like factoring numbers or bin packing or max independence set is actually possible to solve with this technique?
This is a great question. Let's see if I have a backup slide. I do not. It depends on the problem instance. So there are different classes of graphs. There are different classes of optimization problems. Factoring is a particularly tricky one, in that you are actually able to, I guess, if we're able to find, the prime factors of very large numbers, I probably would not be saying it out loud, right? I don't think we can, of course, but that would be pretty neat. The challenge is identifying which problems best fit onto hardware. So in particular, and actually I do have a slide for this, there is one class of problems which does have an efficient representation, which is something called unit disk graphs, which is that if you have atoms, or vertices, and you have vertices connected by an edge if and only if they are within some distance of each other, right? So for example, here is some graph of vertices, and then the edges are based off of this unit disk constraint, then this is efficiently implementable with zero overhead in our atoms. So for example, this is a picture of, which I think actually comes from our machine, of the atoms and a solution to a maximum independent set of this particularly large graph. However, other problems such as, say, factoring or Kubo type problems or other things usually require some amount of overhead. And this overhead is basically you're able to encode the problem into the configuration of some set of atoms, which we call gadgets. And this graph encoding, you can then solve for the maximum weight independent set of this graph and take the solution to that graph and map it back to the original target program. And the particulars of this are like the amount of scaling you get for this depends on the problem instance. So for example, for Kubo type problems with an all-to-all type connectivity, on today's hardware, we end up having this quadratic overhead, which means that in order to solve these problems on today's Aquila, we're only able to do, say, 10 or maybe 10 or so vertices of the original graph. However, for problems which respect the geometry of our 2D system, right? Say I have antenna placement, but it's a Kubo problem, or say, airplanes flying around and I don't want them to hit each other or something like that. Then if we are sort of have similar geometry to our 2D system, then we can encode many more. Unfortunately, I don't have the plot here, but I actually have there's an encoding for Kubo, which is like a local connectivity Kubo, where it can get up to 50 qubits on today's hardware, or 50 variables with today's hardware, excuse me.
Thank you. Thank you very much.
Okay, I guess that's all that we had. Ron, back with another question. Will you have backends for other quantum frameworks?
For other quantum frameworks like digital computing?
Well,
Maybe
Ron,
can
clarify your question.
If I write a quantum program in Qiskit or Cirq, that can be moved to your hardware?
Yes, I mean, right now
Great.
we're in this analog mode, which is a different mode of operation than what Qiskit can support. But this is definitely on the top of our mind of when we have our digital mode. There is just a huge amount of tools and support, which everyone has built and developed, and will absolutely be using those tools in order to support digital mode. It's a great question. And actually, in fact, probably dual mode as well, right? Where say you use Qiskit to describe your gates and then some other object to describe this analog gate, or an analog every qubit gate.
Awesome. And since dual mode is kind of unique to you guys, are you contemplating any future domain specific languages that are, not framework dependent?
That's a good question. So we are looking at ways to use blockade to describe these analog gates. But again, the idea here will be, say we have maybe some Pythonic version of blockade to describe a analog mode gate, and then you could perhaps merge this with other digital languages. This is a good question. I don't have a very good answer right now, but we were definitely working on it. This is sort of on the top of our minds right now.
And just to be clear, did I understand that blockade is a Julia framework?
Blockade is in Julia, yes.
Okay, all right. So you guys hiring any compiler writers over there?
You got me. Yeah, I mean, this is, in some ways, this is what we're thinking about, right? Like, we are trying to compile quantum programs. Julia sort of has this compiler mentality sort of built in. So yes, this is something we're definitely thinking about.
I'll have to reach out to you afterwards. Thanks.
Interesting. Yeah, definitely.
Okay, so just continuing on, Peter asks, any plans to separate out the analog waveforms on a per qubit basis?
Yes. So this is a great question. Let me pull out the Hamiltonian. So right now we have this analog mode Hamiltonian where we have this omega, delta, and then the Vij. So the Vij is dependent on the positions. This is the interactions. This omega is dependent on the this Rydberg laser, which is right now a global Rydberg laser. Basically comes in from the side and hits every single atom. And we have this detuning term, which also actually comes from this a global detuning comes from that very same laser. But one of the near-term upgrades to our machine is something called local detuning, which is to say that you can select, again, within some constraints which are hardware-based, you're able to select the detuning on each atom independently and specify the detuning as a function of time on each atom independently, which allows for a larger amount of control over the dynamics. So this is a very near-term feature that that's probably going to come out soon.
Okay, great, thanks. So just another question. We're almost done the questions. We're going through the questions, a lot of questions. So Kevin asked, any tensor network circuits?
Great. So I guess this has a few answers. So I guess tensor networks are typically a tool to do simulation. I don't think Blockade has a tensor network simulator in it, though this may be something we're working on. The other option, or the other answer to this is taking a tensor network and backing out some sort of quantum circuit from it. But this, I guess this is a very digital mode way of thinking. So unfortunately, we're not necessarily able to do tensor network-based methods. However, I should say, though, that tensor networks like TDVP and other interesting things can also potentially let us efficiently simulate at least short-term dynamics of our up to 256 qubits, which may be otherwise untenable by other methods. So if tensor networks is one of my favorite subjects, but we unfortunately don't have as much support for that right now. It's a good question.
Okay, so I think this is the last question. If anyone has any more questions, just write in the chat below. But Kevin asked, when do you expect hardware to be competitive in performance versus current classical methods for similar complexity?
Well, I mean, to that respect, we are well beyond what a classical computer can simulate, right? For a certain class of, for example, simulation tasks, where we do quantum dynamics of 200, up to 256 atoms, this is not classically simulatable, right? It would require complexity of order 2 to the 256 in order to simulate these systems. There are some tools which let you, for example, use mean field or other understanding to try and get a base understanding of how this hardware works. But then other exotic phases of matter, for example, might be very hard for classical simulation to accurately capture. Again, you can use particular methods in particular contexts, mean field, other neat tricks to understand these phases. But otherwise, if you want to say do dynamics of these strongly interacting systems, it is very hard to do so with current numerics. I guess this is the big advantage of having 256 qubits is it's very clear that we are able to do particular tasks which are well beyond what classical simulation is able to achieve.
Okay, thanks, Jonathan. So that is all the questions, unless somebody has another question that they want to drop in the last 5, 4 seconds, no 3. Okay, so that's all the questions. Jonathan, thank you for answering all those questions. That was a lot of questions.
Absolutely, and thank you for everyone else for attending. This was a wonderful experience. If anyone is interested in working with us more or wants to learn more, I'm just adding up the last slide here. You can email us at info@QuEra.com, or you can go to our website. We're around. I'm sure you'll be able to find us. We'd be happy to work more and answer any more questions you may have.
Right. Yeah, Jonathan, thanks for that. And just from the meetup community as well, on July 1st is our next meetup with actually Professor Just, who asked that question earlier today. She will be speaking on the algorithmic principle of quantum phase kickback. So just make sure you tune into that on July 1st, Saturday, 1 p.m. Eastern time. That's pretty much it on our side as well. Thank you, everybody, for joining this on a Sunday in North America. I know where you guys are, but this is a Sunday after in North America. Thank you for joining. And Helen, I don't know if you have any last minute comments.
Well, thank you for all of you for the participation. Thank you again.
Yeah, great questions. Thank you for the great questions, guys. That was great. Yeah, and Professor Just in the video cam there, she will be speaking July 1st at 1 p.m. Eastern time. Make sure you tune in for that as well. Thank you, everybody, and have a great rest of your Sunday afternoon. Peace.